Good morning, ladies and gentlemen. My name is John. My presentation today encompasses the symbiotic relationship between the AFM and the SEM. These are both very common technologies that we find in the industry today. Generically, my focus today is more on the application of these tools in the semiconductor line. Just a brief background of what we're going to talk about today. We're going to basically look and explore the scanning electron microscopes, the atomic force microscopes, and the generic applications that we find with these two technologies. And I'll end the talk basically looking at the blurring of the lines between the two technologies and the future moving forward, as we talked about earlier on the FX40. For the sake of argument, today we'll be talking about the NX10 versus a regular tabletop SEM system. So as mentioned earlier, the AFM was developed by Professor Kelvin Forrest-Quate in Stanford University. And the aim of today's discussion is the fact that with the new advances in the AFM, with the independent X, Y, and Z fixtures, we have been able to minimize the noise that occurs during the measurement. At the same time, with the ability to look at the sample topography without overshooting the sample itself, and it's very high speed in terms of the accuracy of recording and to scan the surfaces as well. Concurrently, we talk about the scanning electron microscope. The core of the whole electron microscope is the electron gun, which supplies the electrons that will impact the sample below. The beam is focused basically using magnets to get the beam onto the surface. And resultant, we get different types of emissions off the surface. We have the secondary electrons, the backscatter electrons, and X-rays. Each has its own application. Now, one of the key problems with the SEM system is the fact that it is done in vacuum as compared to an AFM, which is basically an atmosphere. Moreover, there is, with a SEM, significant amount of sample preparation required. That is, because of charging that occurs on the surface, it is a norm that we would have to do a coating on the sample prior to measurements on the SEM, meaning that we would have to put things like gold or platinum on the surface. This basically would mean that the wafers are destroyed, or destructive analysis of the surface, as compared to an AFM, where you just stick it into the system, perform the measurement, and the wafers theoretically can move on. Okay, let's talk about the application. So one of the most common applications for the tool would be cross-sectional SEMs. In this particular instance, we're talking about constructional analysis of a semiconductor, meaning that the engineer is interested to look at how the various layers are stacked on top of each other. So this is, to a certain degree, the core competency of the SEM, because the AFM will not be able to do this form of analysis. However, having said that, the concerns we have is that, again, you need a significant amount of sample preparation before you can stick it into the SEM. You have to cut it, cleave it, polish it, and stain it before all these various structures would be found. The other concern that you would encounter is the fact that there would be some level of charging. So a lot of background characterization has to be performed on the tool to minimize this charging on the surface. Because once the surface is charged, instead of getting a nice image, you end up with a very black image. Another example of cross-sectional work is, okay, it is common in the industry that they will need to monitor the etch rate, meaning that, okay, how long should I etch the surface for? So in this particular instance, they will again cleave the wafer in half and then measure the pre and post thickness that occurs on the surface, where they're looking at the height, the width, and the bottom of the structures. So this is an area where the AFM would excel, because without having the need to cleave the wafer, I'm able to use an AFM and monitor this non-destructively. Additionally, I can also look at the sidewall angles, which cannot be characterized on a SEM system. Moreover, the vertical height that is measured on the SEM is based on a scale. It is not physically measured. It is empirically, we empirically do this particular measurement against a SEM bar. The SEM is basically looking at only a two-dimensional, meaning that it looks at the XY. The Z is not its key competency. Hence, this is one of the strengths of the PIFM. Moreover, in this particular cross-sectional work, they would have to measure at least two sides, meaning center to edge. So basically, in this instance, if you're using a SEM approach, you've really destroyed the whole wafer. However, with the advent of the AFM, with the industrial automated AFMs, which I show in a minute, you have the ability to stick the whole wafer in, perform the measurements without cleaving. And if you were to take the total time, although people would make the comments like, if you use the AFM, it's a much slower process and you scan through the surface. But then in reality, if you think of it, the time taken for you to cut and prepare the sample and looking at two sides, because you have to vacuum down the chamber to do the measurements, the AFM is actually comparable in terms of timing. Here's another example. Now, in today's industry, where we are doing things like true silicon via, where we are doing very deep etching on the surfaces, the methodology utilized is what we refer to as the Bosch process. In the Bosch process, the artifact that occurs during the etch is that you'll find a lot of scalloping on the surface. Scalloping is something that is monitored and something that we have to be able to study, meaning that we have to see what is the degree of scalloping that has occurred. At the same time, what is the eventual last scallop, means just before the surface. Is it a peak or a trough? So in this instance, again, you cross-section the wafer, you look at it. However, as mentioned earlier, it is not the strength of the SEM to be able to do vertical measurements. You can only empirically look at it and says, is this good? Is this bad? Or you have to tilt the whole sample to the side to be able to see or do a relative XY measurements of the surface. So in the case of the AFM, with the tapping mode, you're able to quantify these scallops. Moreover, you're also able to quantify the roughness, the top, the side, and the bottom. So a term that we typically use is called LER, L-E-W or L-E-R, line edge roughness or line width roughness, which is something that this AFM would be able to do relatively easy because that's part and parcel of the measurements that occurs on the surface. At the same time, there is no physical damage because in today's market, we are talking about non-contact measurements. Here is another view of the scallops that basically occurs during the etch process. So which is of interest is at the very bottom. Did I clear my etch? Is there a scallop sticking out there which will affect the transistor that we're trying to build eventually on the surface? Now, one key factor that we talk about is aspect ratio, right? So I will discuss that later on in my talk, but here, for this particular instance, definitely the AFM tip would be able to get in because the aspect ratio is actually is about almost 1:1, give or take a bit. So the depth is also of concern. Again, I will talk about it further later in this discussion. So here we have, what we talked about earlier, the automated inline AFM systems. The charm of the system is that you have the fin so that you can actually put full open cassettes, whatever you need through onto the system. It aligns the wafer, it puts it inside to do the measurements. You have multiple tips available so they can pick and place if necessary. The wafers are aligned onto the system. So as I mentioned earlier, that you can do multiple measurement sites on the same wafer. And if need be, you can pick a different tip along the way for these measurements. Now, we talk about the next topic. Defectivity or defect inspection is part and parcel of the semiconductor industry. So in most cases, what happens is that you send the wafers for the scanning. So you come up with a defect scan. and it gives you a Pareto chart of all the defects that are found on the wafer. But these tools only give you a count. It does not describe what that particle is. So if you're doing yield analysis or yield prediction, you can just say, well, yes, look at this map, lots of defects, but they're small, so I should not be concerned with it. What we have learned over time in the semiconductor industry is that this map only gives an indication of what is found on the wafer. There is definitely a need for you to subsequently perform either optical reviews of the surface, SEM reviews, or in this case, even an AFM review of the surface. Now, why is this important? Looking at this map, it says, yes, you have lots of small particles, so I should not be concerned. So true enough, I stick this into a SEM, and then I look at these defects, and it says, based dimensionally, it is a small defect. It's a little dimple, so it shouldn't be of concern to me. However, with the advent of the SEM, we have the ability to tilt the image, meaning that we tilt the whole sample, and then we re-inspect the wafer, and you find that it's actually a column, not a single particle. This being a column means that this has the detriment of being a killer defect down the road, because it can topple over and cause shorting of the surface. So yes, the SEM is able to do tilting for us to look at the defects, but there is a shortcoming to this particular process. That is why the AFM is much better and excels as compared to the SEM. One of the key problems is the SEM image, as I mentioned earlier, is that it is a top-down column of electrons that's hitting the surface. So if I were to tilt the image, telecentricity is a problem on the tool, meaning that as you go down onto the surface, once you tilt, the location has changed. So you will have to spend a lot more time realigning the beam onto the surface for you to image the structure of interest. So that is of concern. Secondly, with the SEM, yes, dimensionally in the 2D, you can see X and Y. But then in terms of height, the shape, the profile, the roughness, it is not the strength of the SEM. Secondly, if you look at these images, they're quite fluffy, they're quite blurred. The reason for this is this. You are unable to do any sample preparation, meaning that you do not coat it, you do not do any polishing or post-processing of these surfaces before you stick it into the SEM. In this instance, the review SEM, you just stick the wafer as is into the chamber. So what you're seeing is outgassing and charging of the surfaces. So thus, you don't get a very strong image of what you're looking for. Versus if you're using an AFM, because you're able to do a 3D rendition of the particle as you scan through the whole image, you're able to quantify its shape and profiles along the way. So that is the strength of the AFM system. And at the same time, not only do you look at the roughness of the particle itself, you're also able to describe the roughness in its surrounding areas. Next, we talk about scratches and pit formations. Scratches occurs for various reasons along the process, be it during the chemical mechanical polishing of the surface, where you have ripping of the surface. So as seen from the SEM, yes, I can see that indeed you have scratches on the surface. You can describe how long the scratch is in terms of the cluster of defects. But then you actually cannot quantify the depth of these defects. So again, the AFM system shows its strength in this instance, because as you scan through the image, you're able to look at the depth in X, Y, or whichever dimensions you want to look at. Now, why is this important? It's because moving down the road, the engineer can say, okay, I have a scratch. I shall now attempt to buff this scratch away, meaning that I'll go in, I'll polish it again, or buff it again. Then after that, when I come back, I need to quantify it. Has the depth of the scratch or pit become shallower after I've polished it? So the SEM can only see a pit. It cannot describe the quantities of this pit. The sidewalls angles, has it improved or has the depth improved? Right. So with the AFM, I'm able to see both the 2D and 3D renditioning of the defect of interest, which is the unique capabilities here on the AFM systems. Now, lumps and bumps. Lumps and bumps, it is part and parcel of the processing as well, right? So from the yield engineer's point of view, they need to quantify, hey, where indeed did these particles come from? Did it come by during the process? Did it fall on from the process chamber itself? So not only do we need to quantify the size, the shape of these defects, we need to know where it came from. Hence, this is where the SEM excels because of the ability to do the EDX of the surface. The energy dispersive X-ray, as I mentioned earlier, is something that is unique to the SEM because upon impinging the surface with the electrons, X-rays are evolved, meaning that as the relaxation occurs, these X-rays come off. And with the suitable detector, you're able to quantify what elements are found on the wafer. But having said that, again, with the SEM, you can see the particle. You may be able to analyze the particle, but you cannot tell how rough is the particle, what's the shape of this particle, meaning that, you know, three-dimensionally, what is the shape of this particle? Right. So here lies the strength here, that, you know, I'm able to describe the shape and size in the SEM. But with the AFM, I'm able to have more pertinent details of the particle in question, right? However, in my latter part of this discussion, we talk about what advances are found to circumvent these particular issues of detection of the elemental or molecular structure. Now we just digress for a second, right? Initially, we're just talking about scanning electron microscopes and AFMs. I will now bring in another thing that is found in today's market for the interest of the general public is the white light interferometry, or we also call it optical profimetry. In the past, we have physical profilers, meaning that you use a needle and you just go across the surface and quantify the surface. But that basically leads to scratching. So in terms of the white light interferometer, it has its benefits, particularly in this instance where we're talking about MEM structures. Here, these are structures that are released on the surface so that they are not flat, but they are protruding up in mid-air. So the question is, okay, why would we use an AFM if I already have white light interferometer? You know, it's also three-dimensional. It is able to quantify height. In fact, it even can quantify scratches and roughness. So what is the distinct difference between these two technologies, right? At the same time, you know, as I mentioned, you know, you are able to do three-dimensional, you're able to look at trenches and all this wonderful stuff with white light interferometers. So what is the difference? The difference lies in this, that the scale of what we're looking for, right? In the case of the AFM, we are talking about a scan area in the micron range versus compared to the white light interferometer, which is in microns or even in millimeters per se. Yes, in both cases, as you note here, it gives a measurement of roughness. But at the end of the day, which would you prefer or which would you trust more in terms of accuracy? Definitely the AFM brings to us a much more accurate and quantifiable measure of the surface as compared to white light interferometers. In terms of white light interferometers, you notice in this particular slide that if the surface is bold or warped, you know, it may give an incorrect estimate of the surface roughness as compared to the AFM, whereupon because you're looking at micro leveling or micro roughness, and you're able to almost go down to the atomic level as compared to the white light interferometer. Another reason it's able to do such a large area is because you're stitching the images. So stitching itself also complicates the matter and creates more error in the whole measurements. So thus, the AFM is still the golden standard for roughness measurements moving down the road. So next, we talk about the future of the AFM. Right? Earlier, we talked about the fact that it does not have a way to excite the surface for us to do EDX measurements. However, there is a new innovation that is found on the AFM, which is known as PIFM, which is photo-induced, meaning that with a laser that excites the surface, they're able to quantify the molecular level contaminant, or what is the molecular structure of the device, meaning that this is very similar to a measurement in the FTIR regime of the surface. Right? The idea is that because the beam is at the tip, basically it's just a regular tip of an AFM, there is a very narrow region by which they're able to, using the light, they're able to excite the surface from using photons, and they're able to make the detection in terms of a force that is found as in the typical AFM measurements. So this is an example by which you're comparing the FTIR versus the PIFM. Notice that the peaks are very good. There is very good correlation between the two methodologies of measurements. So in this particular instance, they have a polystyrene sphere on top of a mica surface. And all the peaks do line up. So as in this particular table, it shows the strength and the advantage of the PIFM in terms of the size, because the AFM itself, we're talking about very small particles, right? That we can analyze as compared to, let's say, even an EDX, where we're talking about in the micron scale, as compared to, in this case, we're talking about nanometer scale, and there is that level of accuracy that's found. And as mentioned earlier, it is just an attachment of the exciting source of a laser. There is no major changes to the system, and it just uses the exact same AFM tip and detection systems on the system. So change is only constant. Change. So in terms of the viability of the tool, they are still symbiotic. We need them for certain instances, but at the same time, there is a blurring of the line between these two technologies with the advent of new systems and new applications and platforms that we talked about earlier. That in the past, people would just think, well, AFM is slow, I can only deal with very small samples. But then now with the industrial scale AFMs, I'm able to stick a whole 12-inch wafer into the system and perform the measurements without any destructive component to the whole matter. And with the scanning speed going up, it is comparable whether I'm using a SEM or a AFM to do the measurements. However, there is another problem that occurs. On the left, you see this instance by which we have very high aspect ratio, meaning that these pillars are 5 micron versus a depth of 250 microns. Now this, unfortunately, is outside the realm of the capabilities of the AFF because the tip will go in and won't come out. So that is where the strength of the SEM still exists, right, for these structures. On the other side of the fence is that with the advent of the 7 nanometer FinFETs, right? FinFETs in their nature are 3-dimensional in shape. So the AFM finds its strength here because you are able to quantify the fins on these FETs as well as the source strain measurements, right? And these are all in the nanometer scale. And in this, as mentioned, this is non-destructive, meaning that you can stick these wafers in, perform the measurements without having to damage these structures. And basically, with the FinFETs, we're talking about very expensive wafers. And with 7 nanometers, you can just imagine how many transistors are there that needs to be measured at any one time. So I thank you again for the organizers for inviting me to do this presentation. I hope it is of interest to everybody, and I'm open to questions at the moment. Thank you very much.